So with we eventually managed. And I promised to call Miraf and tell her that we made it. Just a second, I'll call the secretary and tell her that we managed. Hello? Hello?
Hello.
Hello? טוב, אם לא שומעים. שנייה, אני שומע אם זה לא עבד. מירב, זה עובד. כן, ביי. אוקיי. So, here we go. Here we go. Okay, so last time we spoke about Riemann sphere and the linear transformations on the Riemann sphere. So I remind you what we did. We looked at the complex plane slightly different. We, instead of looking at it as a plane, we decided to fold it into a sphere, bringing one additional pole to the complex plane that is called north pole. So instead of a normal plane, so to say, we added one more point which we called infinity, and on the plane, this is a very large circle, and it's an infinitely large circle. And we mapped a plane to a sphere, but what we called stereographic projection. So each and every point on a sphere was projected on the plane by a straight line that starts at the north pole. So if there's a point P on the sphere, then we draw a line that starts at the north pole and goes to the point P. And whenever it crosses the sphere, that's the stereographic image of a plane to the sphere, and vice versa. And what we also did, we looked at the transformation, particular transformation, W equal to 1 over Z, and we realized that on a complex plane, this transformation has a pole. It has a special pole, which is singularity at the origin. At Z equals 0, this transformation has a pole. Of the order 1. However, if the same transformation is started on the Riemann sphere, then all points are absolutely analytic on the Riemann sphere. And what this transformation does, this transformation actually rotates the Riemann sphere by 180 degrees around the x-axis. So that was a quick reminder of what we did last time. Now, what I'm going to talk today, I'm going to say that this transformation is just a particular example of a more general class of transformation called Möbius transformations. Möbius transformations. This is a class of transformations in complex analysis, very important. And this particular transformation is just a prototypical example of such transformation. So today we're going to study the properties of this transformation slightly in more detail. And let me still focus on the same transformation W equal 1 over Z and see what else can we say about this transformation? Okay, and one of the property of Möbius transformation, I announced this property in general, and we go and see it through this particular example, is that Möbius transformation maps circles and line on the plane local and
דימה, אתה מדבר? אנחנו לא שומעים אותך פשוט.
כן, גם כאן זה נתקע.
תפתח מצלמה, יונתן, מה כיבדת אותה? תפתח אותה.
רואים אותי בכלל?
So let us look at the
דימה, נתפסת לנו עכשיו. זה כמה שניות.
Let us look at the circle somewhere on the complex plane. So let's pick a point. Let's call this point alpha. So this is x and y. This is a complex plane z, x plus iy. And let us draw a circle of the radius r around point alpha, which has a real part and imaginary. So just draw a circle. So how do we, oops, what's now? Okay. How do we describe this circle algebraically? Well, so if you have a circle with around point x0 and y0, that we know that the equation that describes the circle looks like this. So in our case, x0 is a real part of complex number alpha, and y0 is an imaginary part of the complex number alpha. Now let us write the same equation. Let us write the same equation in terms of complex number z and z bar. So let me open the parcel, get x squared minus 2 real alpha times x plus real part of alpha square plus y square minus 2 imaginary part of alpha y plus imaginary part of alpha square is equal to r square. And now I combine it together, so I write it x square plus y square minus 2x real alpha minus 2y imaginary alpha plus real alpha square plus imaginary alpha square is equal to r square. Now x square plus y square, it's z times z bar. X is z plus z bar over 2. Y is z minus z bar over 2i. And therefore, this equation reads z times z bar minus z times alpha bar minus z bar times alpha is equal to r square minus alpha bar. So this is just a simple equation of the circle on the complex plane. Then we can ask what happens to a circle under the Möbius mapping. In particular, let's see what happens if z goes to 1 over w. Okay, obviously this equation becomes 1 over w bar minus alpha bar divided by w minus alpha divided by w bar is equal to r square minus alpha bar. And now I multiply, now, okay, so now if r square minus alpha bar is not equal 0, then I multiply this equation by w bar and divide it by r square minus alpha bar, and I get w bar plus alpha divided by r square minus alpha alpha bar times w plus alpha bar w bar divided by r square minus alpha alpha bar is equal to 1 divided by r square minus alpha alpha bar. And if you look at this equation and on the plane, look on the plane, on the W plane, this equation has the same structure as, where was this? Yes, as the equation we started with on the Z plane. So if you just compare these two equations, you see that these two equations looks alike. There is W bar with a coefficient 1, and before it was ZZ bar with coefficient 1. And there is a linear term in W, and before it was a linear term in Z. And then there's a linear term in W bar, and there's a constant on the right-hand side. So the conclusion from this is that we already know that this equation actually describes a circle. So it means that on the W plane, after the Möbius transformation, this line also looks like a circle. If alpha alpha bar minus r square is equal to 0, then in terms of W and W bar, the equation reads 1 minus alpha bar W bar minus alpha W is equal to 0. Who can tell me what this equation describes on the W plane?
Straight line.
Straight line, correct. It describes a straight line. So we first had a circle on a complex plane, and schematically this circle could be like this. And this is the circle that does not touch the origin. And this circle is mapped schematically to another circle on the W plane. Or you can have another circle that crosses the origin, and this circle is mapped onto a straight line. Under this transformation. Now the radius of the circle R, so let's call it this as R tilde. The radius of this circle R tilde is equal to 1 over R square minus alpha alpha bar plus alpha alpha bar divided by R square minus alpha alpha bar. So this is 1 plus alpha alpha bar R square minus alpha alpha bar. Sorry, this is R tilde square. Okay. Similarly, now let us consider a straight line. Consider now a straight line. Let's see what happens to a straight line with the same logic. So straight line, so we have a complex plane Z, and there is a straight line on the complex plane Z. So straight line is described by equation that looks like A times X plus B times Y is equal to C. So how can we write this line in complex coordinates, the same trig, z plus z bar divided by 2, and y is equal to z minus z bar divided by 2i. Then this equation becomes z times a over 2 plus b over 2i plus z bar a times a minus b over 2i is equal to c, which we can also write as z times a minus ib plus z bar a plus ib equal to 2c. So this is the equation. This is an equation of a straight line on the complex plane. So what happens to a straight line under transformation w equal to 1 over z?
got it.
Equation? Okay, so under the,
דימה, z כפול a מינוס ib זה לא z כפול הצמוד שלו? בעצם?
so there, remember, a and b has nothing to do with a. Sorry, a and b have nothing to do with z.
Okay.
So z is x plus iy, and a and b are just two real numbers. So if you want, you can also write a and b in terms of some complex notation. So you can realize that this is actually a complex number, I don't know, beta. And then the equation will be z times beta bar plus z bar times b is equal to 2c. But that's just to introduce one more complex number. Okay, so let us just skip a and b because we don't need any more notation. So what happens under this transformation? The equation obviously becomes a minus ab divided by w plus a plus ib divided by w bar is equal to 2c, which means that this is equation a minus ib times w bar plus a plus ib times bar is equal to 2c w bar. And we have seen this equation before. So what is this equation? Once again, it depends whether this coefficient is or is not equal to 0. So assume that c is not equal to 0. What does it mean geometrically? If this is our line, what does it mean that c is or is not equal to 0?
If it passes through the origin?
Correct. So if the line does not pass through the origin, this would be the line, then the equation that we found, we can divide it by 2c, and we get equation that on the w plane looks like w bar minus a plus ib divided by 2c times w minus a minus ib divided by 2c w bar is equal to 0. Did anyone see this equation before?
I want to say that this is a circle, but it looks like straight line also.
No, it's if you go back on this equation on the w plane, then you will see, oh, just a sec. If you look on the equation of a circle on z plane here, you see what stands here on the right hand side. It's a radius square minus the absolute value of coefficient in front of z. So it means that, so if we got if we got 0 on the right hand side, it means that r square is equal to alpha alpha bar. So in this particular case, alpha is equal a minus ib divided by 2c. Did we call alpha the coefficient in front of z bar? Yes, with a minus sign. Yes. So alpha is a minus ib times 2c. Then r square minus alpha alpha bar is equal to 0. It means that the radius of this circle on the W plane is actually a minus ib over 2c, a plus ib over 2c, which is equal a square plus b square divided by 4c square.
Dima, can
Right.
you please repeat the last calculation, because I didn't get the המעבר between the dash, the WW bar minus A plus IB to the bottom of the page.
Sorry, first of all, there's a typo here. It should be like this. So what transition didn't you follow, on this page or before?
No, בעמוד הזה, the transition, how did you get from the definition of alpha to this equation?
From definition of alpha to this radius?
Yes.
Okay, because equation, and I can equation. Okay, let me do it slowly. Okay, so I'm writing here. Let me write bar times W minus alpha bar times W minus alpha W bar equals 0. Using the notation I just defined, I'm calling alpha the coefficient in front of W bar. Okay, so this is an equation in terms of W on the complex plane. So far, so good?
Yes.
Okay. Then I'm going back and I'm writing equation that I wrote before, but let me just, for the transparency, write it on the same page we are now. So if you remember when we started with our equation on XY plane and we draw a circle centered around point alpha with the radius r, the equation reads z bar minus z alpha bar minus z bar alpha is equal to r square minus alpha alpha bar. That's what we defined, that's what we derived at the start of our lecture today, when we just draw a circle in terms of complex variables z instead of real variables x and y. Do you agree? Did you follow?
Yes.
Okay, then I just compare this equation for z of the circle that I know this equation describes me for sure a circle of radius r capital. I know it for sure. And then I look at the equation in terms of W, it has the same structure, but it has 0 on the right-hand side. My conclusion from there is that for this equation, I got a circle with some radius r tilde, such that r tilde square minus alpha alpha bar is equal to 0.
Okay.
That's that. So the conclusion is that I started with the line that was not passing through the origin. And under the mapping, I got a circle. And this is the radius of this circle.
So this is the condition for the map to go to become a circle.
Yes, correct. Any line, the condition is any line that does not pass through origin becomes a circle. Any line that does not pass through the origin becomes a circle. The radius of the circle is given by this.
And if the line passes through the origin, then it stays a line in the W plane.
If the line passes through the origin, let's study this case precisely. Let's study this case. Let us now, we didn't do it yet, right? Let us now take, did we do it? It's just, if we take line with c equals 0, then this term will not, so if it passes through the origin, that this term will be non-existent. And therefore we will have a line that also passes through the origin. So let us do it slowly. Maybe it's worth doing it slowly. Now discuss the line that passes through the origin, passes through the origin. How does it look like? The equation of a line that passes through the origin looks like a times x plus b times y is equal to 0, such that x equals 0, y equals 0 lie on this line. Okay, so the equation for this line in terms of z variable will be z times a over 2 plus b over 2i plus z bar a over 2 minus b over 2i is equal to 0, which means 1 over w times a over 2 plus b over 2i plus 1 over w bar a over 2 plus minus b over 2i is equal to 0. So this is w bar a minus ib plus w a plus ib is equal to 0. And as we see on the w plane, this is once again a line that passes through origin. So for line, we get the following correspondence. On a z plane, the line that does not pass through origin becomes a circle symbolically. On w, this is z. The line that passes through origin becomes another, sorry, that's not good. The line that passes through origin becomes another line that also passes through origin. Let me put some coloring. So this is this line. This is this line. So the conclusion is that transformation w equal to 1 over z sends circles and lines to circles and lines. Okay? Okay. I hope these derivations were clear. They're not too complicated. If it was too fast, just do it yourself slowly, and there is absolutely no difficulty in it. Okay, so all what we did right now was totally done on a complex plane. We didn't use anywhere. We didn't use a concept of Riemann sphere. Yeah, so we purely did it on a complex plane. Now let us try to look at it from Riemann sphere perspective. And what can we say? So let us draw Riemann sphere. I'm drawing a sphere. Okay. And I know there is a correspondence between Riemann sphere and complex plane via stereographic projection. Now, there is one property of stereographic projection that will be very useful here. And the point is that stereographic projection also has that same property that if we look on straight lines and circles on the complex plane, what they will become on a Riemann sphere?
If they pass through the origin, then also lines.
Well, there's no
meridians. Meridians.
Okay, so circles. So if you look at the sphere as a two-dimensional object embedded in three-dimensional world, then for us, meridians are just a circle. Circle is being defined as a crossing between plane and a sphere. If you cross a two-dimensional sphere with a plane, you get a circle. That's the definition of a circle. So any circle on the plane becomes a circle on the sphere. And also any line on a plane becomes a circle on a sphere. So actually both circles and lines on a two-dimensional plane corresponds to circles on the sphere. We will discuss what is the difference between these circles, but geometrically.
Only the orientation, no?
Well, curves are not oriented right now. So we don't discuss whether the circle was oriented this way or that way. We just discuss a circle as it is. So circle becomes a circle. And okay, so you can probably guess what will be the main difference between circles and lines, because the definition of the line, that line will always go to the point called infinity. Any straight line will unavoidably reach an infinity on the complex plane, which means that on the Riemann sphere, it will pass through the, it will pass through the northern pole. As opposed to any finite circle, which does not touch an infinity point, and therefore it does not pass through infinity. It does not pass through North Pole. So the image of any straight line on a, well, that wasn't really straight. The image of any straight line on the complex plane will be a circle that passes through the northern pole. An image of any circle that is not that does not go through the infinity. In particular, let's think about a unit circle. It will be a circle on the Riemann sphere. Okay, so let us try to see it in more detail. So Riemann sphere, if you look at this as an embedded object in three-dimensional space, as a two-dimensional sphere embedded in three-dimensional space, satisfies the following algebraic equation. So this is a unit sphere. These are the points on the unit sphere. So now, what I'm going to do a stereographic projection. Let me use a different color. I'm going to take a point on a sphere on the northern pole and pass it through the plane, so the point P on the sphere will become P prime on the complex plane. So let me call coordinates, let me use capital X and Y to denote the coordinates of the point P prime on the complex plane. So P prime has coordinates X capital, Y capital. And I reserve small letters X, Y, and Z for the points on the sphere, seeing as a three-dimensional object. Is it okay? Okay. Then let us try to understand how we relate these two sets of coordinates, x, y, z, three-dimensional coordinates of the point on the sphere, and two-dimensional coordinates on the plane. So this is point on a sphere. This is projection, stereographic projection on a plane. So how can we relate algebraically these 2 points? Okay, so let us, okay, so now it depends on your geometric imagination. You need to understand what this stereographic projection does, but essentially, let me try to argue that if I look at the plane P, at the point P, and I'm just sending a vertical projection, these would be coordinates x and y of the point, and these will be a coordinate z, right, of the point on the sphere. So what would be coordinates x and y? So to see that, we need to draw a following triangle. I'm trying to draw it. So this will be a triangle. And from this construction, you see that both points x and y, x not capital and y not capital, scale the same. So they're being multiplied by the same number. So I can look at this triangle. I can look at the triangle at the cross section. So at the cross section I'm now describing, my Riemann sphere becomes just a. So this is a cross section of a Riemann sphere. This is a north pole. This is the point. This is the point we called P. This is the point P. And we are starting the projection of this point onto the point P prime here. So this is the point P. This is the point P prime. And I choose a point, say with y equals 0. So this is on the x-axis. And the coordinate of this point is z. Now I need to identify the triangles, the similar triangles. So these are my triangles. So there's this triangle. This is the red triangle. And there's another triangle. And you probably can see from this drawing that these triangles have identical angles. This angle is equal to this angle is common angle, and this is 90 degrees. So let me call this point O, this point, let me call it, has a coordinate x. This point has a coordinate x large. Okay, I think I have all points I need, and then I have a relation O to x or O to x capital. It's the same as point. Oh, okay, let's call this point some. Let us give a name for this point. Let's call this point, I don't know, D. As D to N, to O to N, and this is 1 minus Z divided by 1, which means that OX is equal to OX small divided by 1 minus Z. which means that coordinate x is x small divided by 1 minus z, coordinate y will be y minus z. So these are coordinates x large and y large. So on the complex plane, we have a number x capital plus I y capital of a point x, y, z on a unit sphere. And I can inverse this transformation. I can say that point on the unit sphere x, y, z has the following components: 1 plus x squared plus y squared, 2x, 2y, x squared plus y squared minus 1. So this is this transformation in reverse.
Can you explain again why you did the transformation for a capital X and capital Y?
Explain again what point? This relation.
Yeah,
Just say loud. What do I need to explain? I'll be happy to explain. Just say it, what needs to be explained.
how did you get to this conclusion? That what is this transformation? You know, you have a new variable that is dependent on x and z, and another that depends on y and z. So it's
Right.
and the
So
z,
are you happy with the equation in the blue frame? So this equation needs to be explained, or this equation is clear?
no, the one below, that z equal to capital X plus I capital Y. So Z, it's not the same, it's capital Z, yes? It's not the same.
All right. Sorry, right. It's yeah, in this notation should be capitals. It's a point on the complex plane, yes.
Okay.
Sorry. Okay. Okay, so now let's see what happens. What happens if we draw if we draw a circle? Let us draw a circle on a complex plane. So I'm drawing a circle on the complex plane. So as you say, there are coordinates x capital and y capital, and let's draw a circle around origin just to make life easier. R cosine phi, R sine phi would be a circle around origin of radius r. Then the coordinate on the Riemann sphere will be x, y, z. And now I plug this thing into our equation. It will be 1 over 1 plus r squared, 2r cosine phi, 2r sine phi, r squared minus 1. And obviously, what this thing describes, it describes that z component is a constant, so it describes a circle that goes along the meridian, and it has a radius 2r over 1 plus r squared. So this is obviously a circle drawn at the height r squared minus 1 divided by r squared plus 1. So conclusion, a circle on a complex plane remains a circle under a stereographic projection, or mapped on a circle on a Riemann sphere, in other words. Now, if we look, now let's see what happens Now let's discuss the line. So let's now have a complex plane, and let's discuss the line y x. Let me just draw a line y equal x to keep things simple. So then point x, y, and z on a sphere will be 1 over 1 plus 2x squared, 2x squared minus 1. Now, what is this? What is this line? So first of all, we see that its x component and y component are the same. So you need to imagine that it's something that happens on the cross section of the sphere. And I claim that if you, okay, now let me try to draw it. So if I go back on Riemann sphere, so this is our, let me use a different color. This will be our x-axis, y-axis. So I need to go somewhere here where x is equal to y. So it will be roughly, it should be a circle that lies on the plane x equal to y. So I need to cross the Riemann sphere with a plane that goes like this, with a plane x equal to y, and then I'm getting a circle again, and you can check that this is the circle, because if we take Riemann sphere, x squared plus y squared plus z squared equal to 1, and demand that we are looking at the cross section of the sphere with a plane x equal to y. So this is a cross section of the sphere with this is a cross section with this plane. Then we end up having an equation 2x squared plus y squared, plus z squared is equal to 1. And now we can substitute these guys into this equation, yeah, and see that we are getting 1 over 1 plus 2x squared times 2 times 4x squared plus 2x squared minus 1 divided by 1 plus 2x squared, and I bring it together and I get 1 over 1 plus 2x squared times 4x squared plus 4x squared plus 1, and this is just 1. And therefore, we see that line, so conclusion from here, line turned into a circle that passes through the northern pole. Okay, we looked at it through the examples because it's easy to show it on the examples rather than to give a general proof. However, the claim is that the most general Möbius transformation W is equal to AZ plus B divided by CZ plus D. This is the most general Möbius transformation. Has the same properties. Has the same properties as the 1 over Z transformation that we discussed, because you can always decompose Möbius transformation into 1 over z and some linear and a combination of linear transformations. And because linear transformation send circles to circles and lines to line, then the Möbius transformation also does the same. So when can we say about general Möbius transformation? A general Möbius transformation corresponds to the rotation of the Riemann sphere. And our particular Möbius transformation 1 over z was a rotation with respect to x-axis by pi. So what it means that it is a rotation? It means that if we draw a sphere, that's our sphere, which is essentially a representation of a complex z-plane via stereographic projection. So you can either treat this as a sphere, Riemann sphere, or you can treat it as a complex plane z, which is connected to the Riemann sphere via stereographic projection. So if you apply Möbius transformation on a z-plane, then there is a w-plane or another Riemann sphere. Geometrically, it's easy to think about it as another sphere. And Möbius transformation is a mapping from the first Riemann sphere, from the Riemann sphere on the left to the Riemann sphere on the right. And it corresponds to the rotation of the original Riemann sphere with respect to some axis by some amount of degrees, by some angle. So let us try to specify the transformation and see how many parameters do we need. So when we start our transformation, we had a special point which is a north pole and a special pole which is a south pole or original sphere, and there is a north pole and the south pole of our target sphere. So what can we say about Möbius transformation? I remind you, Möbius transformation was AZ plus B divided by CZ plus D. What are the special points of this transformation? What special points can you point out?
Z equals minus D over C.
Z equal minus D over C. This is a pole of the transformation. So there is a point somewhere here, schematically, which is minus D over C. Z equal minus D over C. It lies somewhere on the sphere. What can we tell about this point? Where will it go? Under the Möbius transformation. Where this point will be sent. Think about a particular example, 1 over z, it might be easier. Think about a case w is equal 1 over z, and in this case, this special point is equal 0. Where would it go?
To the North Pole.
To the North Pole. So this point will become that point of the new sphere W. There is another special point here, and this special point, let's choose a different color. It's z equal minus b over a. What is this point on the original sphere? Somewhere here, there's a point minus b over a. Yeah? Where this point will go?
To the South Pole.
The South Pole. So this point will go there. So these 2 points, we already know where they would go. It does not fully fixes their transformation. We need 1 more point. So schematically, I need 3 points. So let me draw it. W is any Möbius transformation looks like this. And what this means, that point Z0, it's the point where W is equal to 0. And we know that this will go to the South Pole. Point Z infinity, it's where W is equal to infinity in the sense of Riemann, and this point will be sent to the North Pole. And there's a point Z1 which just happened to be fixed, and it go to 1. The last point is not particularly special, just I chose 1 extra point to fully specify that transformation. I could have chosen 2. Okay, so any questions about Möbius transformation so far? Okay, so let us see. So question number 1. If there are 2 Möbius transformation, say W of Z and psi of W. What is the composition of these 2 transformations looks like? Please share with me your ideas.
So we said that W of Z, the general Möbius transformation, can be written as some
Like this.
yes. It can also be written as it can be separated into a part that is dependent of Z and a part that is independent of Z.
Right.
So maybe we can say that well, it's not linear. It would be inverse of Z, right? It's not, because you'll have to be Z in the denominator.
Dima, can you ask the question again? I missed you.
What is the combination of 2 Möbius transformations? So imagine you have 1 Möbius transformation apply after another.
Just if Möbius transformation is connected to rotation, maybe it's just take the sum of the rotations.
Correct. So that's precisely the point. So Möbius transformation is a rotation of a Riemann sphere. So if you have a sphere and rotate it with respect to 1 axis, and then rotate the same sphere with respect to another axis, what you will end at the end of the day is another rotation. So any combination of rotations is a rotation. You probably learned this in many times in courses of classical mechanics and quantum mechanics. So rotation, the combination of rotations is always a rotation. And since Möbius transformation corresponds to rotation, the combination of Möbius transformation is a Möbius transformation. Okay. Or if you're more mathematically inclined, Möbius transformation form a group. So composition, so in words, composition of Möbius transformation is again another Möbius transformation. Another point which is very important, and it has to do with the angle preservation. So imagine a sphere and imagine there are some circles on this sphere or some lines on this sphere, but it can be two circles that cross at an angle alpha on a sphere. And we already know that these two circles on the sphere, they represent lines. They represent lines or circles on the complex plane. So these two circles on the sphere, they represent lines or circles on the complex plane, depending on whether they cross original on the complex plane. Now, what happens with the angle alpha when I turn the sphere around?
Alpha shouldn't change under just rotation.
Correct. So just under rotation, angles don't change on the sphere. So any crossing line crosses at the same angle before and after Möbius transformation. So, but now I know that these lines on the sphere, they have one-to-one correspondence to the line on the complex plane, which means that the lines that were crossing on the complex plane before Möbius transformation at the angle alpha will cross at the same angle after Möbius transformation. So angles between crossing line are preserved. Angles between crossing lines on the complex plane in parentheses on a Riemann sphere are preserved under Möbius transformation. Now, okay, there are many functions that preserve angles at some part of the complex plane, but the point is that Möbius transformation, the only transformation that preserves angles everywhere on the complex plane. So it's the only transformation and I'm not proving it, I'm just saying it, is the only one, only transformation that preserves angles globally, meaning everywhere on the complex plane or on the Riemann sphere. Okay, and one last point, as we see, Riemann Möbius transformation can be always be written in this form. So I can identify and specify this transformation by writing this coefficient as a matrix. And then you can show that two, so let's call this coefficient say 1, 1, 1, 1, 1, 1, a composition of two Möbius transformation. So then the composition of two Möbius transformations can be represented by a product of these matrices. Sorry. So from mathematical perspective, we have defined a group, linear group. Okay. So these are the main properties of Möbius transformation, and I think I more or less managed to deliver all what I wanted to talk about today.
If we reverse the orders of W and Xi in the last row, we flip the matrix multiplication.
Correct. Correct, and that's the meaning, and these transformations are not commutative, obviously. So it's a very nice representation, and these transformations they're related to many things in physics. They're very useful in many areas in physics. In particular, everything that has to do with spin representations. You know, spinors. You probably start learning spins in quantum mechanics, haven't you?
Glanced over the general. We didn't really talk about.
Okay, then just believe me for now. So that's okay. So just a mathematical concept for now that will be extremely useful for understanding spins, particles with spin. Also very important in context of superconductivity, topology, lots and lots of things in condensed matter physics. It's one of the fundamental mathematical arenas to play this very convenient mathematical tool. Frequently appears as everywhere you have topology. Spins geometry. Very often needed for physicists and very fundamental for mathematicians. So I think it was a very nice example to understand how you can look at a complex plane at the same time looking at it as a Riemann sphere. I think it shows some advantages of thinking about complex plane as a Riemann sphere, geometrically, and dealing with the point infinity in the same way we treat any other point. It shows this big advantage of Riemann construction. I think it deepens the understanding of complex analysis. Okay, do you have any more questions or comments? I remind you that I'm available on my office hours, which is at 11 a.m. Thursdays, I believe. Yeah. So ב-11 בבוקר בימי חמישי. So if people want to discuss things or have questions, you are most welcome to join. And if nobody comes, I just waiting there for like 15 minutes or so, and then I go. I don't I don't write indefinitely. Okay, so I guess that's it.